sharing my screen. This is sharing screen, so I hope this will stay the whole lecture in. Hello guys, and I'm happy to see you safe and well. I hope others will join in a minute. We are not full class yet, but the recording will help if someone was not able to connect because of bad internet or anything else. What do we have today? Look, I have many screens waiting. So 1, 2, 3, 4, each one is for different purpose. I'm gonna move between them and let me start with the course. And what do we have here? What's new? We have two links, new links. The shift operations here. And there is the bitwise operation. This is the program, a Java program. We're gonna go through a little bit and apply some of these on bitwise operations. We are doing chapter 10 today, and chapter 10 is supposed to be somewhere in here. So this is chapter 10. I don't need this, so I put it down, and now we keep our screen as clean as possible, and here we go. So instruction sets and characteristics. Where do we start from, do you think? Do we go through these one by one and check things, or do we start somewhere else? I prefer to start, like if I were in person in class, I will start back into this set of instruction set. This is an instruction set, you know. This is an instruction set. Did it have any shift operations? Then we're gonna see this in the chapter, guys. Shift operations. Yes, we had shift operations here. Left shift and right shift operations. There are more. Yes, in contemporary computers there are more. But even the monument machine, first machine did the left shift and the right shift operations. About characterizing those operations in the instruction set. Remember, there are 21 instructions only, and now these days we talk about 500 instructions and more with multimedia and everything new anyways. They are grouped into data transfer, you see. So when we say data transfer in the lecture, in the slides, remember that loading and storing are mostly the data transfer. About branching, conditional and non-conditional, these can go together in contemporary computers now, guys. They are jump operations. But the difference between this and this is that in contemporary computers, we don't have a lot of these anymore. We don't say go to anymore. In Fortran language, when I started, we learned Fortran, they used to have more than 5 go-to statements, and they are spread all over the program, and then you have to jump from location to location. Not anymore. Conditional branch, guys go with an if statement. We know how powerful if statement now these days are, control statements. So you might want to change this with control, you know, loops and if statement are control statements. Here in Von Neumann, they call them conditional branch. You see, if, so if the one that we know, if there is no loop here, no, this loop, sorry, this type of instruction with this type of instruction, they make the loop. And we did a program like this or two in the class. Arithmetic operations, very important. But I want you to notice one thing, guys, here. That there is no float, there is no double, there is no Boolean types, there is no, it's just integers and sometimes with a carry put in MQ. This is all overflow, not even carry. Overflow is put into the MQ. If you read these correctly, I mean, specifically, then you will notice that ما في شيء اسمه double point something, decimal point, ما في. So the data type. Is there a string to worry about here? Do we take, for example, string functions like we do now in Java for index of and substring? No, 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 nothing like this. So there were no data types in here. Now these days we have data types. Address modify, we don't have these anymore. No, we can enter data directly to the computer at any time we want, and then we can move with the addresses with an array. No arrays here. This might sound like an array, guys, if you notice. This might sound like an array. You have list of numbers, and then you change the address, so you are picking the next address in memory, the next address in memory. This is genius, guys. If you really want to understand computer architecture, then you understand what you see here. It has everything. No, not everything. I mean, text and multimedia and something. No, but I mean the essential power of a machine is there. So they could have done anything they want in that programming language, in that machine instruction set, but with difficult programming. You might say, but yes, we have characters and digits, because when we say load MQ, this is string, مش هيك? Remember, guys, we don't say load MQ. We write binary. The first program I wrote to you in the semester when we were talking about this machine was purely 40 bits of zeros and ones. So this is the idea. So our chapter is talking about this in general, but most of the ideas that I mentioned here, you will see there and plus more. So I'm gonna do this down, and then if we go here and see what they want to talk about, this we know. What's missing here, guys? The interrupt cycle, right? So there could be an interrupt cycle here. It doesn't matter for this. Instruction, machine add, subtract, machine code, human add. This is a 16-bit computer, guys. Look, the word is 16-bit, 466. Now, these days we go with 64-bit computers, which means instructions can be of 64 bits length. And this will give more space for what, guys? Not too many opcodes. Opcodes needs maximum of maybe 10 bits for 1024 different opcodes. The rest will go for more memory to go through, and still not enough. Still not enough. If I have two operand, both are addresses. Oh my God. Let me start explaining. So I start from here also to explain. Oh, where do I go from there? Let me see. What did I prepare here? What did I click on? Let me see. I didn't click on anything. Okay, let me go and see. Where is that? It says online. Yeah, here. I even prepared an online whiteboard. I'm getting better, guys, in doing these online. And look, if I have a 32-bit 32-bit computer, and then I have here 10 for the opcode, and what am I left with? 22. Suppose I say here 11 and here 11. Suppose. What is the maximum memory address that I can get to? Question. Who's going to answer that? Please help me out. What is the maximum RAM I can get to? 02. Come on, guys. Somebody say something. Okay, you don't want to say anything, and it's 2 to the power 11, because this could be accessing memory, loading something and something. I divide them evenly, just pick for something. They can be in different ways. So the question is 0 to 11, that's only to what? 2 kilobyte? 2K addresses, 2K. Lano 10 is 1K. That's the RAM that we have now on some of our computers, because some of our computers are still 32-bit now. We have 64-bit, but still running 32-bit. So this is strange. What happens with this for 32 computers to keep working, guys, for memory that is more than that? We will see later that something called indirect address. So the memory will go further. The memory will go directly from the instruction set. You go only to this space, and here you have 0 to 31 bits. And when you come to one of these addresses directly from the instruction set, this is an indirect address. It will take you to 232 bits address. So you see, this is not data, this is address. So address taking you to address of 32 bit, and then going to 32 is 4 giga, 4 giga. I hope you understand. I hope you understand what I'm talking about. So here, the size matters, but كمان the design matters more. Instead of this, if I want extra here, I can say that I can cut them into 16. And what's left, guys? 8 and 8 instead of 11, 11. So this might take me directly to 16. So 2 to the power 16 will be having more direct memory, because direct memory will take less time to access the data. Instead of going first to memory, bring the result into the CPU, then call again and get the result there. One thing I'm sorry, I don't like about this is seeing your faces, Looking at your faces sometimes will help me to keep explaining or stop explaining, or I don't know. Okay. So let's see. So it's very important, guys. But the number of operands. These are 2 operands. Can I have more, guys? Of course I can have more. So if I want to do something like this, guys, if I want to do something like this, allow the user to write A equal B plus C plus D. In this case, guys, then I need, it can be done in 2 ways. Either the compiler will cut them into 2 operations, يعني B plus C أول, بعدين the result will be put into plus D. So I have 2 operands here. Only B and C are being used. And also I have to put something for the, for the destination. So if I do this as, let's say, B, this will make it less, guys. So this can work on 2. ليه؟ لأنه B can go here first, and then C can go here first. They are added, temporarily put in a register inside the CPU, inside the set of registers inside the CPU. Then the program will continue, will take this, which is still in AC most probably, and then we'll take the D from here, and then we'll add them, and then it will put the result in B, which is the starting address. It was here. We will see some samples of these programs and in a better, neat way. Okay. Data processing, data storage, data movement, AI, program flow, if statement, a jump, loop, something like this. Data processing, what is this? Math operations we saw in Von Neumann. Data storage, store and load, still there, and then IO is there. These are the type of instruction that we have. Here, 3 addresses. This is what I was talking about a minute ago, guys. Operand 1, operand 2, and the result. So equal A equal B plus C. Maybe a 4th next instruction. This forget about, guys, and implicitly it goes with the PC being incremented after each fetch. You understand what I'm saying, right? We said when we fetch an instruction, we increment the PC, and we don't have to store the next instruction in the instruction set. It's not common. A equal B plus, need very long word to hold everything in there. 3 addresses. But let me not agree with him because there were some computers, guys, with four operands. They don't have to be values, you know, they can be used for other purpose. For example, the computer VAX 11780, it had like five, if not more, operands in the same instruction. Okay. So two addresses, one address, implicit second address, usually a register accumulator common on early machines. This is exactly von Neumann, guys. This is exactly von Neumann. What did we do with the von Neumann? We said load M17 and then what? It puts it in AC, then add M18. Here it is, guys. Implicit second address, usually a register accumulator. So load M17 is storing the first number in the accumulator, usually accumulator, and then the second operation that has one um, operand in it, add M18, it's one operand, M18. It will take whatever in 18, it will add it to AC, and will put a result. So one number, one address machine, one address machine. And there is this, guys, wow, zero address machine. What is that? What is he doing? C equal A plus B. Push A, push B, add, and pop C. Let's see here. Is there a clear screen here somewhere? Is there a clear screen? No, I didn't check it very well. There's supposed to be في وحدة بس ما في let me see. I can do this بس it will take معلش يلا لأنه they're supposed to be there. Maybe there are 15 screens I can go up and down with. I'll check that. Anyways, يلا I'm doing this for a minute. خلاص خلصت. And now we go to pencil. Where is the pencil? This is the pencil. A equal B plus C times D. Can this be done in a zero operand, guys? So here we go. And we usually use a stack for that. And then B and C and D are numbers here. So what does it say? Push B. So B will be here. I'm sure you've seen this in what? In 204. And then push C. And C will be here. Whatever number is in C. So it could be 5, 3, 7, whatever. And then push. You need to push, guys. You cannot say multiply D because this will have to bring D from the RAM or from somewhere. But we don't this because we are using stack. So you have to push. This is the idea. And you have to push D. Now B, C, and D. Now you know that stack work on the top of the stack. So once you say here multiply, it will take the whatever is in D with whatever in C. It multiply them. You see zero operand, and then it delete the top and it puts the result here. So this is R. This is R. And then it continues, مش هيك? And then it says add. What will it add? It will add the result of B times D plus whatever in B, and it will take this out. It will take this out, and it will put the result R again. And now you say show store or yeah, why not store or pop. Pop. Let's use only stack terminology. Pop shoe, pop into A. So pop this. So only push and pop will have one constant usually, and it will work fine. Okay. Let me check this guys. هون كان عم بيقول لي شو هون حط لي هون. Let me see. 16, 17. No, I thought it's doing something for no. Okay.
Doctor,
Yes. Do you see a clear?
yes, we're seeing clear. بس إذا بدك في هيدي هون ما بعرف إذا قادر تشوف شو رسمت على السكرين. إذا كبست على هاي بعتقد بتقدر.
Hey.
إيه
Okay.
إيه هي.
Okay. Thank you. Very easy. Very easy to clear. Thank you. Thank you. Thank you. Okay. Now, what do we have? So, two address machine, one address machine, zero address machine, and this introduced for you. More addresses. Now we start talking about which is better, and there is a big debate here, guys. Let me tell you about it. When I talk about, let me show you. Wait a minute. Look, the type of operations, guys, here. Data types in von Neumann, no data type. Now these data types are integer, double, text, يعني string, and so on and so forth. Length of the opcode field, I started with that. Number of addresses I talked about, whether it's two addresses, we talked about that here. I'm jumping to explaining this idea. Number of registers come in important. Let me talk about this لأنه we were talking about how many registers and something. They come all together. So let me talk about RISC and CISC. Go back to this, here, and RISC and CISC. So RISC is reduced instruction set computer. But I must have started with CISC because CISC started before RISC. CISC is in the market way long before RISC. RISC is new with respect to, but anyways, ماشي الحال. CISC is complex instruction set computer. Okay, in here they say, I want my instruction to be simple. Simple. يعني opcode and maybe one or two maximum. Okay. In CISC, they say no, it is open in my case. So opcode, OP, and addresses as I want. In RISC, they say in this instruction set, guys, ما هو opcode بعدين مثلا add something, delete, I'm sorry, add something, subtract something, multiply something, and this and that. The only reference to memory, listen carefully, guys, this is very important. These are called power computers, by the way, power computers. And they are in the market if you want to buy this kind of computers. They say the only opcode that allows to access memory operand is the load and store only. Load and store. These can go with something like, guys, memory of 17. Even in von Neumann, you were able to say, for example, add M of 18. Even in von Neumann, here they say, no, don't do that. Don't do that. Why? Because, guys, you know the back and forth going from memory, fetching, data, a number, and then do the operation will take time. So you cannot say add, you cannot say subtract, you just do on register. Fazan, this could be register 1 and register 2 only. While in CISC, as we know, they allow you something like this. So you can do this with this, with another memory location. So you can say operand like add memory location 1 to memory location 2 and store in memory location 3. How many times you have to go into memory in this case, guys? 3 times to get the data. Wait a minute. If I'm adding this and one of them is destination, then yeah, كمان I need to store. So it's 3 times at least. Suppose I want to add whatever is in M1 with M2 and store on M3. So load, do the operation, and then store. This is 3. Okay. Let's see what's going to happen here, guys. If I want to add those 3, what do I need to do? I need set of registers. Then I say load M of 1, just like in the previous case. So I go to memory and I put the result in one of my registers. Okay? Now load M2, you need to load the numbers. You cannot get out of load and store. Load M2, it's another, and then the RISC computer will add them up. And then there is a store in M3. Oh my God, then I'm going one more time to the RAM and storing the result in here. What did I save? I saved nothing. Okay, this is what they tell you. Afterwards, as long as you are working with whatever in memory 1, طبعا in variable names in contemporary computers, guys, when you say N و M و I و J, this is what we mean by variables. Anyways, once you load these numbers in the registers, if you come to do, for example, after that, مش هيفي بعدين لنقول divide, we did the result in M3 مش هيك؟ Divide M3 by 5. This is a constant. This is possible. لأن one operand can be a constant, one operand can be a memory location. Anyways, طبعا in von Neumann ما كان فيه هيك. So now, in sys computers, you have to load this again. You have to load it again. So you have to go to memory one more time. In this computer, they say, since you already have stored M3 in here, then we kept it for you. We didn't allow any other value, and there could be here some instructions between them to delete M3 from the register. We keep it for you for later use. I don't know how much I'm getting to you guys. I just
أكتر
yes.
بس فينا نعمل شغلة لأنه أسيل حكيتها على الجروب والظاهر ما شفتها. هيدول
لا,
هون
I'm not looking at the chat لأنه I can't look at the chat and
بس
talk to me please.
هيدول الآتس عم بيزعجوها، فبليز إذا فينا نقرب السكرين شوي هيك.
هول الادز ما فيني لأنه this is online. ليش عم يزعجوها؟ شو بدها فيه هون؟ عم تطلع فيها هي؟ Yeah.
Doctor, why don't you use the Zoom whiteboard?
Zoom whiteboard, it's affecting my performance with the Zoom itself, you know. So this is why
you have to choose it from the share screen itself.
طب
It
هلا
says
is it
separately.
better? Is this better since we are there? Is this better? I increase the size of the screen.
It's still quite distracting.
Still distracting? يا عمي I'm gonna cover it all in all. Can you see my still distracting?
انا شايفها عادية صراحة ما فيها شيء.
Instead of concentrating what I'm talking about, you look into the
okay. خلص مش الحال عند أسيل دكتور. Thank you.
Okay, thank you. Just listen and concentrate, and I'm trying to use the visual aid I can do without even this. Whatever I'm saying is important. Listen. I repeat the last idea in order for you to understand what I'm talking about. لأنه risk and CISC is very important idea, guys, that you must learn. Because now they are fighting which is better, risk computer or CISC computer all the time. we said we have an instruction like this in this computer. This is allowed. In RISC computer, you cannot write this. What you need to do is load M1 as one instruction, load M2 as another instruction, and load M3. So these are three instructions, simple. So when you see in my lecture simple, this means simple, load, load, load. But there are many. So more instructions, yet simple instruction set. This is complex instruction set. Look, it's loading three and adding all in one. It makes it maybe easier for the programmer, but then the compiler and the computer has to deal with separating them and doing this and doing that. Okay. There is a slight idea that I want you to understand. So I load M1. I load M2. I'm talking RISC now. I load M3. So they are loaded. They are loaded into the registers. Now, when you say insist add M1, add M2, add M3, كمان you have to store them in registers. But here you might have only 2 registers available to you. So you bring M1 in and you bring M2 in, you add them, you get the result back into the RAM, and then you maybe load M3 in one of the register, keeping the other register empty, and then bringing the result back in here, and then finish the storing of the result into the RAM. Here, the same thing, load, and then do the add, add this with this, blah, 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 finished. And then now we want to store, so we store. They cause the same difficulty. They cause the same time of execution. Look what we are talking about now. Same time of execution, but simpler instruction set, load M1 لحال, load M2 لحال, more instructions in the program versus one instruction complex, less number of instructions, yet more complex instructions. You will see this in the lecture, in the note, in the PowerPoints. Now, since they took the same time, guys, what is the idea behind RISC computers? They say the following. If I can create a 32 registers for you, I can make a 32 registers for each program or process running. Look, here, no, there is like 3 or 4 registers only for each process. And there is context switch, if you remember. So you move these 3 out, and then you use another process, the same registers in, and then. For each process, guys, look at the huge number of registers in RISC. For each process running, I have 32 registers. So when I load M1, suppose it's the N is residing here. M is residing here. A of I is not a memory location, it is a memory location, guys. It's a variable. It's here. A of 0, A of 1, A of 2, A of 3. They are all being stored once, loaded once. Later on, no matter how long your program goes, whenever you want to reference N, you don't go to RAM to get it again. Whenever you want to reference M, you never go to the RAM again, because you know that once you load something, you're not going to use it for one time and that's it. Most likely. Sometimes yes, but most of the time, when we load something, then it will be referenced a lot in my program, and saving all those data inside the CPU with 32-bit set of registers for each process running, then this will save time going back and forth to the RAM, because you know the speed of the bus affects the speed of the RAM, affect the CPU. So load once and use many, rather than load once, use it, and if you need the place, bring it back to RAM, and then get another one, back and forth, back and forth, and back and forth, and they are fighting. I don't know. I don't know if you understood the idea. Okay, someone should ask me, how come these 32 registers are in the CPU at the same time? Fine, we increase the number of registers in the CPU, no problem. We put cache in the CPU. Cache could be 1K if you remember, right? Level 1 cache, it's inside the CPU, so it could be 1K. Why don't we save allocation for 32 registers? This is very easy. Okay, now N1, program 1 is running, or process 1 is running. It has all those 32 registers. Now what happened? Some P1 asks for I/O. You remember? An interrupt handler. Process 1 goes out, context switching happen. When we talk about risk, it doesn't mean we change interrupt cycle and everything. It's just talking about instruction set and how they treat the load and store statement compared to the other instruction in CISC. So it goes out, and then another process comes in. When we do what? When we do context switching, guys, and P2 comes to work, then another 32 register will be available for P2. They go into a cycle like this. We will see this later, maybe in another chapter. These 32 registers are for the first process. Another 32, I'm gonna mark this as a start and end. These are for process 1. When process 2 comes in, it gives another 32 registers for it. And this is the end of it, and it keeps going. So we might end up having 128 registers, something like this or more. This depends on the multi-programming degree that we have on our computers. Now, when this is full, guys, what's going to happen? Then these will start moving out of the CPU. It takes out those, it stores them with P1, like in normal context switching, and use this one for مثلا P15. And life goes on. When we start going back from processes, this will be deleted, go back, this will be deleted, go back, and everything is finished. Risk and CISC, please read about them for those who wants to learn. There are tons of material that you can look into and see and learn about risk and CISC and why this and why that. Okay, maybe we'll talk about this one more time in sequence chapters, I will see. Addressing modes. You remember when I was talking about indirect addressing? This is maybe in chapter 13. So addressing modes to reach further location on RAM beside the main area that we can reach it from the operand of an instruction. I mentioned this, and I drew, and then I deleted with the eraser. Okay. Addresses, numbers, characters, logical data here, bit wise, and flags like booleans and something, they were not in there. Bits operation, let's talk about this bit operation, and then what, and this. And then maybe we'll finish. We'll talk about bit operation and the shift operations that are available to us. So I'm gonna go down here and then go to another screen. And where do we go first here? We go with the, okay, Eclipse. Eclipse, if you remember. I hope now you are happy because there is no, whatchamacallit, there is no ad on the side here. We never programmed something like this before in Java. Maybe you did on your own, I don't know. But we have something called bit operation, guys. Bit operation. If come in, I go back one more time to this and go to this and thank you, Lana. And here, if I have an integer 10100, okay. It is what, guys? It is 1, 2, 4, 8, and 16. This is a 20 in decimal. Okay. It can be treated as bit. It's not an integer number. It's bit that means something. It's a bit that means something. It's a bit as, and so on and so forth. They can be used as bits. And we have something called bit operations, like left shift and right shift. We have seen this even in von Neumann. So what kind of other bit operation I can do? If I have two of these, whether they are the same length or not, guys, I can have them less. But anyways, let's do them like this. Then even in Java, guys, we have the and the OR and the XOR operations on these. So if I have here 1, 0, 1, 1, and 0, when we do the AND, what we will get, guys, as a result? So this and this. Where did we use this, guys? XOR, for example. We use it when we were doing
SEDT.
single, yes, thank you very much. Single error detection and correction. So you might use this in your program. If you are doing it in Java, you can use this, guys, for the final word to see where the error is at. So if we are doing XOR, guys, let's do XOR. Hey, what will be filled here? Come on, remind me. 1, Mark, thank you. لأنه we need XOR to be even numbers. So even number of ones, this is 0. This is even number of ones, so it's a 0. This is odd number of ones, so this is 1. And odd number of ones, so this is 1. This is 1, guys. So you see, they are handy. And we have them on our computers. So we never did practice something like this. So now it's a good idea to introduce them. So if we have this is AI generated, by the way. I didn't write this code. I just asked AI, and it gave it to me. A equals 60. This is the binary number 60. B is 13. This is 13 in binary numbers. C is just a variable, and here we go. I need to go. I don't know if this can be moved to this side. Yes, so I can see. And here it is, guys. Integer dot to binary string. Yani now it's not considered as 60 anymore or something. It's considered as 1100011110. So A and B here. And it's printing the result. If we go and run the program now, you will see the results one by one. And here, if I go and now I can see this side, I keep moving back and forth. And you see here, binary representation, this and this. A and B is 12. Let's not go back and forth all the time. The syntax here is very easy to see, guys. A and B, one and is for the if condition. So this and is the operation for bitwise operations. C equal A and B. And if we add them in front of us, guys, here, let's add them. طبعا, they have to be one after another. 0 and 1, the and, what does it do? It needs both of them, yani, and to be the same result. So for the result of this, 0 and 1 are different, so it's 0. 0 and 0 are the same, so it's 0. 1 and 1 are the same, so it's 1. 1 and 1 are the same, so it's 1. The rest are 1 and 0 is 0, and 1 and 0 is 0. Yani, I don't need, guys, to go, I think, let me do it one time only. here. But we already did that, guys. But we did it on similar numbers. So 1, 0, 1, 1, 0, and then I'm not going to do the 4 4. That's it. Suppose I have only this here, 1, 0, 0, 1. So with the AND operation, guys, these are assumed to be zeros. So the result is 0 all the time, you see, because these are zeros already. So with the AND, they don't show zeros. So 1, 1, this is the AND, this is 0, and this is 0, and this is 0. Both of them should be the same. Zeros will become zeros, 1 will become 1, and this is how we go about that. So this is the result. For the OR, guys, one of them is 1, so the result is 1. 0 or 1 is 1. 0 and 0 is this, the rest is 1s. I'm not going to go through these because you know exactly what. I have a question for you. Who is going to tell me how to calculate, if you don't see this as a result, minus 61? Who's going to tell me how can we tell that this is minus 61? I'm gonna copy paste it, right click, can I copy it? Yes, into here, where? Here, clear, and right click and copy image. No, image copied, what? Copy what? Right click, ما في غير copy image, save image as ما في. I was
You cannot paste
The
on.
text
I cannot paste, huh? I cannot paste.
can, but you need to add a text box.
Okay, so
right.
where is the text box? Here?
Yes.
And now plus, and right click and now paste. Copy image, no. I go back and do it one more time. Maybe this will help me, but if not, then I can live without it. From here, right click, copy image. Do I take it as ما في image? So let me say copy, ما بعرف. And one more time into the online and inside the text, copy image, no. Copy image, save image, no. It's not working. What? I don't know. Download? I don't know. I'm not gonna download anything here. No. So let me not use this for the time being. Let me do escape here. I don't want it anymore. So go back. Now will this copy? No. خلاص, I don't want it. Okay. So I go back to here. Who's gonna tell me how to calculate this, guys? What do we do? Just the procedure. We talked about this when we were talking
Use
about.
complement.
How? Just read it. How do you read it? It's already in 2's complement, my friend. But how do you read that this is minus 61? I can read this as minus 61. How? Okay. They are 32-bit, remember? And I want you to remember, guys, that there is 2 1s and 4 zeros afterwards. Where are we? Here? So it's like 1 1 1 2 3 4 and the rest are ones. صح ولا لا? Okay. The last one is what? Is 1, it means it's a negative. This is in 2's complement. It's a negative. How many bits do I have? 32-bit. مش هيك? 32-bit. So it is 2 to the 32. I don't care. I don't care how much. It's like 4 giga. 4 giga. مش هيك? Suppose. Oh, it's 2 giga and one going for the positive. I mean, this number. What is the largest number that can be presented here, guys? This is for sine. This is for sine. So this is 2 to the power 31. واللي هي شو أكبر رقم ممكن يكون هون؟ شو كنا نقول مليار billion, I don't know in English, مليار شو it's 2 giga, 2 مليار. Now this is minus how much? This is 1, this is 2, this is what, guys? This is 4, this is what? 8, This is what? 16. And this is what? 32. So all these are ones، يعني بياخدها بيجمعهم كلهم مع بعض، بس شو بنقص منهم؟ بنقص منهم هول الارقام اللي هن zeros. If you add these up قد ايه بيطلعوا؟ 10 20 60 so it's minus 60. Are you okay? I talked about this before. انه this is two's complement I know, but how do we read them? How do we know it's this is negative? All these are مثلا this is 2 to power this is 1 this is 2 بيجمعهم مع بعض كل هول ده وبنقص منهم هيدا الجواب اللي هو بتاع minus 60. Okay, this was said before, now I say it again. So this is we will talk about in a minute. This is shift left مش هيك؟ Shifting left. There is a difference. This was in my slides. Where is the slides now? If I go back to slides, no, I don't want slides. I minimize this. I go to this, and this is the shifts, guys. The arithmetic shift hold. I'm talking about these now. Okay. Shift 2 times to the left. What number we are shifting, guys? We are not shifting the minus 61 or something. Calculated wrong. I got 60. I go back and check what 61. Did I calculated them wrong? Maybe. I will check later. مهم. Shift twice. طبعا in Newman it was shift once and then you execute it many times. Now here we have this option of shift twice. What's the number we are shifting? It's 60. So we go back to here where shifting what? A. So this one. Shift left. What was it? Yeah. Shift left. How does this work for shifting left, guys? Shift left means take this out. Bring this one all the way to the left. Bring this one all the way to the left. Bring this one all the way to the left. يعني you are shifting and add 0 to the right. يعني add 0. The number becomes 111000. 111000. And what's that, guys? 1 محل 0 1 2 4 4 8 16. No, 1 2 4 8 16 and 32. What's 8 16 and 32? Back to 60? No, it's different. So we lost one of them. So what I'm saying now, they are, one, wait a minute. So there is one, okay, 0 1, this is 2. There is a 0 here, 1 2 0 1 2 4. This is 8. This is 16 and 32. I don't have somewhere to write 2, but let's do it there. Let's do it here. There were not a 1 here. I have to look out the 61 that he has for 8. Do I have 1? I don't have 1. He's saying 61 is supposed to be the answer. I have to check that. Okay? I have to check that. This is 1 and 2. This is 3. So, okay. I will check that. Why it's not 61 as an answer in my case. And why he's saying 61. What? You have to take the whole number and then subtract from it. Okay. I have to take the whole number. Maybe you take a smaller number and show you the 2's complement of that because I have to calculate all these and then subtract from them this number and then get the number. I don't only add these. Okay. Wait. We were talking about shifting left and I think the number was 11100. Was it like this, guys? And this is not a 60. I was starting from 60. Let me go. Going back and forth is very difficult. I think there were one more one. Are these 60? This is 1, this is 2, this is 4, 4, 8, 16, and 32. Yes, these are 60. So now this is 60. I'm shifting one time. What did we say for this will go out and this will come here. This is 1. Shift left, Michelle. And this is 1. And this is 1. And this is 0. And this is 0. And I introduce a 0 at the end. So these are 6 bits, 1, 2, 3, 4, 5, 6. And these are 1, 2, 3, 4, 5, 6. So now what's the answer? This is 0, this is 1, this is 2, this is 4, this is 4, this is 8. So this is the 8. This is 16, and this is 32. Okay, and the answer is 8 and 6 and 20. So it moved 1. So the 4 is out. Yes, so the 4 was out from shifting left. But this is supposed to be shifting left. When I shift left, okay, let's go through this one more time. I don't like the numbers, so look what we are going to do. We are going to do into this. And there is a shift left, logical shift left, and there is a arithmetic shift left. Now, talking about this shift, guys, that I was talking about, you see, you take the last number to the left and you throw it out, and then you move these to the left, and then you introduce 0 in front. This is what I was doing. Does it say here anything about result? No. So it's just simple shift. Why do we use it? I will tell you. So it was correct. We lost the 4 and we ended up with a number that logical shift left. It's like divide by 2. This is what I'm talking about, guys. I was expecting that the number would be half of 60. What am I doing wrong? Please, if you can help me to see. Now this is 0, shift left, well, shift right. Shift right will divide this, multiply by 2. Did I get multiplied by 2 when I shift? Well, it doesn't say multiply by 2, this one. But usually when we shift left, it's like we are increasing the number of ones to the left, and this is like shifting by 2 to the left, which leads to multiply by. Does it say here anything about multiplication by 2? Larger register, we will use 6-bit register. It doesn't say. After shifting, we have the result. Let's take this number, guys. What was it before shifting? It was 1 plus, please somebody write down and give me the answer. 1 plus 8 plus 16. This is 2, afwan. This is 1. This is 2. 2 plus 8, 10. This is 26. Is he saying 26 here? He's saying 13. How come?
26 is the answer. 13 is the original one.
Okay. So the original one is here, and this is the result, you see? So this is multiplying by 2 when we shift left. So the original number is 1 and 4 and 8, and this is 13. And when we shift left, it becomes 2. Now, if I go back here, why it's not doing what I know, what is wrong that I'm doing, that's not doing what I'm doing. So this is the original number. Let me clear. I said 1, 1, 1, 1, and 0, and 0, and 2. This was the number. And what did we say this starts from, guys? 1 and 2, this is 4 and 8. Please tell me if I'm doing something right. This is 4, this is 8, this is 16, and this is 32, right? So this has got to be, this is 20. No, I know maybe. Maybe, okay. This is 12 and 16 is 28. So this is 60, right? We mentioned that 60. Now we are shifting, logical shift left. So we say, you know what I'm doing wrong is that these are 4. So these are 4. This is what I'm doing wrong, guys. No, this is what I'm doing wrong. I'm leaving this one to go out while there is a space for it. So when we are doing left shift, we have to go with the number of bits that are in that number. So if they are bits, we use, if they are 8 bits, then we use 8 bits. If they are 4 bits, then we use 4 bits. And now it's going to work properly. So this one will go here. Now it works, guys. And this one will go here. This will stay as 0. This one will go here. 1, 1, and then 0, and then 0, and we introduce a new 0 coming from out. This is what we saw a minute ago in the notes. So I was doing everything correct, but I was killing this one, and it's wrong. So now what do we have? We introduce this 0, so this is the number. 2 zeros, 1 introduced, so this is 0. This is 1, this is 2, this is 4, this is 8, this is 16, this is 32, and this is 64. And now if we add them up, they're supposed to come out to 120. They're supposed to multiply by 2. 1 and 2 and 3, these are out. 8 and 16 is 24. 24 plus 32, قد بيطلع 56. 56 plus 64, this is 0 and 120. It's correct. So this is the operation for shift left. Logical shift left. 1, it goes twice. No, I mean, if I go back to the program, I'm not gonna continue with the rest with this. I'm gonna go back to the shift because I'm running out of time. So this one, guys, what did it say? Shifted twice, مش هيك? When it's shifted twice? Shifted twice, the original number was 240. Well, equal, this is the answer. The original number was what?
Original was 60.
60? Now multiply by 2, that's 120. Multiply by 2, that's 240. And this is the answer. Okay? Okay, fine. So the rest are bit operations, guys, as you know them. Look here, the minus 60 that I got is there, minus 60, but I don't know why he got 61 before the complement one. This is the not 61. Wait a minute. The 60 is with this one. So one more here. I have to check that, guys. I have to check that. You work on it, come in, please, yourself, and see the 2's complement of that. It becomes 61 rather than 60. No. This is not the complement. This is the not A. Which is not A. Yani the negative of minus 60 is minus 61. The minus of 60 is minus 61. 2's complement. لأنه we add 1 to, I remember. So you take this and you add 1 to them for it to work. I'm not gonna waste my time on that. لأنه I have a few things to explain more. And if we go to this to continue, 10 minutes, wait a minute, to continue with these guys, then we saw the arithmetic shift left. It multiplied by 2. If we do the logical shift right, it's the same, guys. So this 1 or 0 will go out, and then we move everything to the right, and then we introduce a 0, so the opposite of this one, and this comes out to be the division by 2. This is what, by the way, von Neumann does. Left shift once and right shift once, and he did them this way, even from that time, guys. Other operations that your instruction set can have is circular lift, the circular left shift. This has less usage, but it is important for many reasons. And here we go, guys. What happens is that you take this to a temporary value, you put this here outside to implement it as programming. So you take this zero out, you مثل sort routine. You create a temporary location, you put the zero out, then you start moving these to the left. هلا هنا حاطينها باثنين بس هي shift in one. So the zero is out in a temporary, then the one will go to the left, the zero will go to the one, da. Now this is duplicate, you bring the temporary here, and this is circular wait. If I remember correctly, we did something like this in Java 1 as a program to do circular wait. Circular wait now the opposite way, and this one is important, guys. This is with the arithmetic left shift, because you have to keep the sign. You have to keep the sign. Look what's going to happen. This is the number, and then this is positive, لأنه 0 is positive, but this is signed number, and 0 will stay in 0. So the sign stays there. This will go out. So it's the same, guys, as we did before, but you start from the number, not from the sign. So you keep the sign, and then you start shifting left, and then you introduce 0. This will keep the sign and shift the number to the left. One more, and this is negative number, guys. So you keep this, you delete this one, you get it out, ما بدنا إياها, and then you shift left, and you introduce the 0 to the right. كمان it works. This one is important, guys. كمان arithmetic right shift. Look, the same. So you keep the 0, and whatever is in here, if this is 1, you keep the 1. If it's 0, so it's different from the previous 0 to 0, 1 to 1. No, 0 to 0 or 1 to 1, and you take the number here, whether it's 1 or 0, and you move it, and you get this one to the right. And the same here, if it's a 1, you see, it's the same one, but instead of 0, 0, he put 1, 1, and he kicks this one out. Okay. Where do we use these shifts other than in here? I have time. Yes, I have 5 minutes. Look at this, guys. What? Okay. If I have a 32-bit number, whatever, and the bus is only 16-bit bus. Oh, is that possible? Yes, it is possible. So this is 32-bit, and this is 16-bit bus. I want to transfer, this could be a buffer, guys, where a buffer in the I/O module that we talked about, or in the DMA module that we talked about. So the bus connecting the CPU to this is 16-bit, and yet the buffer is 32-bit. The data is waiting here. Then what happens, guys? The device will fill the buffer, and then 16-bit has to be transferred. طيب. We take the first 16-bit on the bus, and we send them wherever we want. What about these 16, guys? What happens? What happens? How can I transfer these 16? I cannot move the bus lines here. What I need to do, I do a circular wait, circular shift, عفوا. So I do circular shift, 16 times. So these 16 bits will move to the right, to the left, عفوا, and this will come to the right, then I transfer them. And then what do? I shift them again 16 times, I go back to the original data if I want them. Just answer me for the last part. Is it okay? Is it clear? Why we can use something like this in building computer architecture, computer organization, and something like this? Anybody can please tell me that? Yes, it is clear? No?
Yes, clear.
Yes. Okay. Mark, anybody else? Levon, Yasser, usually you talk to me, usually. Guys, physically on the bus ما قلنا في بس هيك ومش قلنا بعدين بيوصلوا مع الدي ام اي جايز، مش هيك قلنا خلينا مع الاي او موديول. شو بدي الاي او موديول؟ مش هيك قلنا اي او موديول؟ مش قلنا هون في ديفايس اي او ديفايس؟ طيب الديفايس بعت المعلومات لهون، قلنا هون في بفر، مش هيك؟ هيدا البفر، هيدا الباص اللي رسمناه as one line. It's not one line, guys. I say assume that this is 16 lines here, and this is 16. So how do I transfer 32 bit over 16 lines? ما هو إذا كان في بفر هون معناته only 16 bits are، بس the device sent 32. So the first 16 will move on the bus going to the CPU or to the RAM if we are storing in the RAM. And then how do I transfer these? The bus cannot move to these 32 bit. These 32 bit have to move here. So if I rotate them 16 times, yalla, then this will be here and this will be here, and then transfer them. Once we finish, if we need to go back to the original number for any reason, we do another 16 times shift and it will go back to its original situation. Wow, this is tiring, and I hope you are getting as much information as you need from in person. What's good about this, guys, is it's recorded, so you can see it more than one time. I'm going to stop recording now. Where is the stop recording? Stop recording. Where is the recording? More. This is the more. Stop recording. Stop recording. Yalla, and yeah.